So in today's session, we'll be performing the automated docking using Python, and we'll be running in Jupyter Notebook. Okay, so I'm not going to explain how this Python, how you can build that Python script. Okay, so but I'm going to tell you like how you can use the Python script and where you have to do the changes so that you can get the results. Okay, but I will explain you how it works. Okay, because learning Python in itself takes time, and it won't be, I mean, you know we won't be able to do it in in this one session. Okay, so I will be sharing the script, and you can use the script. Okay, let me just share in the email. Okay, let me just go to it in to just share you an email. Just a second. So if you have downloaded the uh, Anaconda software and install it, you can follow along with me. Okay,
Sir, what is the name of the software, sir? What is it?
Anaconda. So
Have you sent the link, sir, to the software?
yeah, I have sent a link in the first day itself. So
First day itself, you just sent the link for Mastro.
oh no, I'm send it. Anyway, I'm sending you the link again in the message.
Okay, sir.
In
Okay, sir. Can you send me, please, sir? Again.
Anyway, so if you have not downloaded, it takes time. It's a huge uh, software. The size is large, so you can download it later on. But anyway, I'm sharing the script just now. Okay, just give me
Sir,
1 second.
okay, sir. I just received two messages from your side, sir.
Okay. Yeah.
The
I
first,
think I think you joined late, I guess. That's why. Anyway,
on the
I'm
first day only, you have sent the messages through the mail.
yeah, I
20th
will
alone.
forward again. Okay, no issue.
Okay.
Okay, I have shared the script in email, and you can download that, and you can follow along with me. Okay, so if you go to this Anaconda, you can just download this software, and for Windows you can download this one, and according to your system you can download it and install it. Okay, once you have installed it, you'll be getting an application like this. Okay, so you just open this, right? And Okay, here are some of the applications present in Anaconda. So we are going to use Jupyter Notebook. Okay, so in order to open this, you have to click launch. So when you click launch, you will be it will be opening a web browser. Okay, so in this web browser, you'll have the option to select files. Okay, so this is the default directory for that Anaconda. So I have sent the uh, script for running the automated docking. So if you have downloaded, you can let me make uh, this working folder. Okay, for this session, today's session, let's say automated docking, right? So this is the script that I sent you. So I'll just copy it here. Okay, in the working folder for today. Fine, this is our working folder for today, automated dash docking, right? So if you want to open that file, then what you can do is you can go to this upload option and then go to show all files and navigate to the file. Okay, for me I have stored here, right, automated docking, and select this file and click open. Okay, so now it will be uh, you'll be getting the file here. Okay, just refresh this and somewhere it will be there. Too many things are there for me, so this is the one, right? 17 seconds ago I've just uploaded this file called virtual screening underscore Vina. Okay, so you can double click this. When you double click this file, it will open it, and this is the script, and we'll be following along all this script. I will explain this. So anyone trying along with me, or shall I just go ahead and start explaining? Okay, Milan, are you following? Are you have you installed the software?
Hello, sir. Can you repeat the Jupyter Notebook part again? Like, how did you open this interface?
So, have you installed it, Milan? Have you
Hello.
installed the software?
Hello, this Anaconda? No, it's actually
Uh,
installing it.
all right, fine.
Oh, this is okay.
Fine. I will repeat again, okay? So I'll just,
Thank you, sir.
yeah, sure, no issue. Let me just, okay, after installation, you'll be getting an application. If you go to this start application and then, you know, type Anaconda here, you'll be getting application like this, okay? So click open. Right, so when you click open, you can see many application available inside Anaconda, but for now, or for us, we just need the Jupyter Notebook. So this is the Jupyter Notebook, and you have to just click this launch button to open this. Okay, so when you click this launch button, it will open a web browser. In my case, it's opening in Opera. Okay, in your case, it may be Chrome or Mozilla, whatever you have installed or given preference to. So for me, I have given preference to Opera. Okay, so now you have opened the web browser using Jupyter Notebook. Okay, so what you can do is you can upload the file that I've sent you. Okay, the file that is the script for automating the molecular docking workflow. Okay, so to do that, to upload that, you have to go to this upload option. Okay, so when you click this upload option, you will be able to browse the file that you have saved. Okay, so here in the working folder I have kept the file, so you just have to select this file, then click open. So when you click open, it will be imported in this particular folder of Jupyter Notebook. Okay, so in my case it is um, uploaded here, so I can just double click this file. Okay, so when you double click this file, you'll be getting some kind of interface like this. Understood? Yes.
Yes, sir.
Okay, fine. So the same thing that we have done in command line also, you have to set the path to your working folder. So if you want to access the file that you want to do docking with, you have to keep the application path to your working folder. The same rule follows here also, right? So let's copy the path of our working folder using from this address bar, copy, and then you paste it here. Okay, so this is some kind of library called operating OS. Okay, so it allows you, when you import this library, it allows you to change the or do some of the things that you are able to do in command prompt. Okay, similar to command prompt. So in command prompt you write cd or d colon, right? The same thing, we are using this OS function to do the same function that we did in command prompt. Okay, so don't worry about this, just remember that I'll be sharing, I have already shared this, the first line that you are seeing here. Here you can change the part of the working folder. So you just replaced whatever part already was there, okay, with your current working folder path. Okay, so this is my current working folder path. But see, this is backslash. Okay, but for this script to run, we need the forward slash. Okay, this command to run, we need the forward slash. Remember that. Okay, otherwise it will give you error. Okay, so once we have kept the path of your working folder, you need to just press this play button. Okay, so when you click this play button, it's like pressing the enter button when you are doing the command in the command prompt, right? So when you want to execute the command that you have written in the command prompt, you enter the enter button, right? Or you press the enter button, the same thing. So you can just press this play button, then it will execute the command. Okay, it's already executed, so nothing is showing. That means it is successfully executed. Otherwise, if some errors are there, then it will show the error here. So if I want to show the path, see, this is different, right? November 6 something. So if you want to show the path of my current current path of this application, then you can just use this command and then click the play button again. So see, now it got changed to my working folder path. Okay, so this is the ligand preparation step. Now we are going to do a ligand preparation step. So yesterday what we have downloaded, so let's do from yesterday's work. So the second one, right? Where was the Okay, let's see. Okay, let's take this one. Okay, FDA molecule. And paste it here, right? So let's convert this into PDBQT format, split this out. So you have to split this molecule. So imagine the same thing can be done using what? The command prompt also. So I will tell you the difference between using the command prompt and using the script. Okay. So let's say you are doing this by command prompt and you use OpenBabel now. Okay, OBabel, and then what? This FDA file. Okay, sorry, I'm in a different path. So let me change the path to the our working folder. Okay, right. So OBabel. Babel, then FDA minus capital O, and then let's say let's give some name, right? Out dot PDBQT. So if I n minus m, right? So uh, it contains around 1400 molecule in this single file, right? So we have to split this file into individual files so that we can get all the uh, molecules or the drug molecule present in this file, right? So that we can dock one by one using Autodock Vina. So when we do this, the same thing can be done using this script. But the thing is, let's imagine that this is like millions, this file contains millions of compound. So the size of this file will be more like, right, like 1 GB something kind of size will be there. So when you try to execute this command, when you have that kind of large or enormous library database, most probably your system will crash or it will hang, because it will load all the uh, system memory or the random accessible memory and use all those memory to first you know uh, convert it, then extract it, and it won't do one by one. So it will be trying to convert all the molecule, and after converting all the molecules it will then start writing. So when it converts, it will be saving the converted file in the memory. Okay, so it won't be saving directly to your hard disk. That means it will take much memory. Okay, so it will, obviously it will crash your system if you are using from the command line. But here in the script, you see, I will explain again. Okay, but here in the script we are just taking the molecules, the whole molecule, but we are splitting them one by one. Okay, we are splitting them one by one. We are taking the first molecule, then we are, after taking the first molecule, we are just if you need require energy minimization, but in case of Jing database downloaded file, most probably you won't be using the energy minimization. But anyway, if you require it, then you can use this uh, particular line. The same thing, we are using OpenBabel and all the flags that were required to run the minimization command. But the only thing is we are splitting one molecule at a time, minimizing it, storing in a temporary file. After minimization, you go for this changing of the or conversion of the file format. Then you can do the charge addition also. And if you don't have hydrogen atoms, you can add the command for adding the hydrogen atom. So you can just copy this here and you just change this into H. That means you are adding hydrogen atom. Okay. Anyway, let's remove this for now because we know that this molecule that we have downloaded from Zinc database contain hydrogen atoms. So let's not keep that. So you can add the charges also. So Gerstinger charge we are adding. But what we are doing is we are saving the first molecule in a temporary file. So this temporary file will be again taken, and this will be this temporary, it's like a container. Okay, the first molecule it takes and keep this in the container, and then it is converting the file format, adding the charges, and then saving in a hard drive. Okay, so it is doing conversion for only one molecule at a time, so it doesn't take up the memory of your system. So it is taking the memory as for doing conversion in our this command prompt for one molecule only. So it doesn't take, right, it takes it faster, and it takes only some few, very less amount of memory, right? So with this script it won't crash your system. Okay, and one more thing is it is taking the name, exact name of the molecule. So it will be extracting the name here. If you open in a so it will be taking this name, and then it will copy this name, and okay, we have to extract in individual files, right? So if you do like this, it will be saving as out.pdbqt1 2 3 like that, right? But in the script what we are doing is we are extracting the name, okay, this name, and then saving according to this name of the individual files, so that you don't get confused, and you know when you are docking with this particular molecule, right? So two things that we are doing here. So it will take up less memory, as well as it is splitting and also saving the molecule according to their title or name. Okay, so let's run this. So let me change here. So the first line, so these are some libraries. Okay, so don't worry about this, these are required for running this particular commands. So we already you have I mean I have already sent you the script, so don't change anything else. Whatever you have to change, these are the things, these are the important things that you want. If you are going to change, then here you have to change. Okay, so this is your input file. So in our case our input file is what? FDA, right? That is the input file here, right? And now this is the output folder. Okay, in this output folder you can give any name. I'm just giving as process underscore ligand. So it will create this program. When you run, it will create a folder name process underscore ligand. Inside this process underscore ligand, it will store all the structure that it's going to process, and the converted I mean the molecule with charge is added, right? Energy minimized, right? So if you run this, let's run this and see. So it is running, and if you go to our working folder, so it has created a folder, and inside this folder it will convert all the molecules into PDBQT format. It is already charts are added, and also energy minimized. Okay, anyway, you don't need, but I'm just want to show you that you can do the energy minimization step also. So I just added the step for energy minimization. Okay, because it is 1000 something molecule, it's taking time. Yes, Natasha, yeah. Anaconda is free software only. Anyway, let it run, okay? So in the next, so after getting this particular molecules, right? Converted. See, it doesn't take much memory, so that's why you are able to scroll this and then do other work also. Okay. So if you do with the command prompt, you will be having trouble scrolling this, and system will become slower. Anyway, so the idea is if you even have like huge databases that you have downloaded, and if you want to do docking, so only thing is you have to keep your system up for a long time, but it won't hang or crash, okay, like any other system. Like in Pyrex also, if you are doing docking, when you convert the molecule, it may crash, okay, it may hang, but here in our case it won't be hanging or it won't crash, okay, because we are doing single file at a time. Okay, anyway, it's taking time, so let me explain the next step. So in the next step, what we are doing docking, right? So let me just get where the command is. See, yesterday, remember when we were writing vina.exe, right, the command, and then the configuration file. So the configuration flag is here. Then we have to define the configuration file, where we have to keep the inside the configuration file we have to keep the XYZ coordinate of the grid box center, the dimension, and if you are doing only the uh, one single target docking, you can keep the name of the processed receptor, right? And then the ligand name here, right? And the path, okay? Don't worry, okay? Just the ligand flag and the ligand path and the name, and this is the output, okay? Output flag. Then you will be getting the output file, and this is the log file, flag for the log or the log file. Okay, here is the log file, right? The same thing that we have done for single molecule, now we are using this script to automate the docking process. Okay, so we have done splitting of this molecule, converted all the molecules, right? Fine. But if you start docking for 1700 something molecules, it's going to take time. So let me just take few molecules. Okay, this is like 17, right? Let's do 17, and rest of the molecules I'll just delete. Otherwise, it will keep running and we'll be wasting our time, right? So like this, you can convert for thousands of molecules. Okay, so let me come to the working folder again, and then let's go to the next script. Okay, so here, so it's just saying that we are going to use Vina. Here we have to again define the folder where all the ligands are present, or all the molecules are present for docking, and you need an output folder. After docking, you have to put the molecules, right? The output file, the log files all together, right? So we are going to generate a new folder named docout. You can change this name, okay? Then what it is doing, it is going to go and look in this particular folder containing the ligand molecules, and it's going to take one molecule after another and start docking. Okay, so when you do docking for, let's say, 10,000 molecules, okay, so you'll be getting 10,000 output, or you'll be getting this 10,000 scores. So out of this 10,000 scores, how many top molecules do you want? Okay, right? I mean, you're not going to study all the 10,000 molecules, right? So you're going to study only, let's say, 100 top scoring molecule. So that you can define here, okay? So top n, there's top scoring molecules. So here, if I give 10, that means it will report only 10 molecules out of how many you are docking. Let's say if you are doing docking 10,000 also, it will report only the 10 top scoring molecule. If you give 100 here, it will report only 100 molecules. Okay, so let's just skip 10 here. We are going to do 17. So out of this 17 molecules, what are the top 10 scoring molecules, right? So the same thing that I told you before. So it is doing docking for one molecule. It's taking the molecule that are contained in the processed ligand folder, one molecule at a time, doing the docking in the automated fashion, right? So now after doing docking, so imagine here you have the process ligand. Inside the process ligand, if you have 10,000 molecules to dock, you will be getting new folder named docout. So in the docked out folder, it will contain, if this is like 10,000 molecule, it will contain 20,000 files, right? The file that is output file of the dock confirmation, as well as the file containing the score of the docked of the docking of that particular molecule, right? So there will be 20,000 files containing in the docked out folder. So if you do manually, like if you want to see manually how to compare and then see the highest scoring top 10 molecules, it will take forever, right? It is actually almost impossible to open one by one 20,000 times and see which is the top 10 scoring molecule, right? So in order to see the scores, this this script is trying to get the top scoring molecules. Okay, so if you open yesterday's output from Veena docking, see this log file, right? So in this log file, you see you have this line. Okay, so after this line, the next row is the this particular highest binding affinity data, right? So we are looking for this particular line. After this line, we are looking for that second, or the second column, first row. Okay, so here we are doing that, and we are taking that particular data and taking also the name of the molecule. So when we are saving this particular log file, we are saving the log file according to the name of the molecule. Okay, so we know that this log file contains that particular molecule. So so we are comparing the molecule name as well as the binding affinity, top binding affinity value, and then we are keeping it in a container, and then we are going to list it out. Okay, so sorting here, we are doing it, we are sorting it according to the affinity score or the binding score, and whatever you have given in the this option. If you are giving 10, then we are reporting only 10 molecules then, right? Finally it's writing the file. So let's do docking. But if I run this now, it won't work. Okay, why? Because we need the configuration file to be present in the working folder here, right? Remember when we are doing the single VINA docking, we need the configuration file, right? The configuration file, the ligand is already present, but the receptor also not there, right? Receptor not there, and the vina.exe file is also not there, right? So if you do run this button right now, it won't work. It will say that it cannot run. Okay, some error will be there. See, so what you can do is, let's copy from yesterday's work. So you have this process file vina and then configuration file, right? And go to this automated folder, paste it there. Okay, and then run it again. This hopefully it will work. Okay, it's running, it's working. Okay, now let's open this and see. So it started docking. So this log file, it is according to the name of the molecule, okay, that you are docking. Ligand name. So Jing ID is the ligand name, and if you open this, you can see the uh, scores. Okay, so finally after docking everything, it will create a top scoring file. Okay, so according to that number that you have given, how many you want, it will only take report the top 10 scoring molecules. Okay, let it run. All right, so in the last part here, what we are doing is, this is the again you see here we are just doing 17 or something molecule docking, but if you are doing 10,000 molecule docking, even if you have the list of top scoring molecule, now if you want to search one by one, see, you must be having the name because you will be getting the list of that top scoring molecule, but still you have to search here, right? So you have to write the name here, then search. If you are searching 10,000 molecules, obviously your system will again go slow, and once you find it, you copy it and paste it in some other folder to extract the molecules, the top scoring molecules. So it's manually, it's going to take time if you are docking large number of molecules, right? So in the next script, what we are doing is we are creating a folder named top doc molecules. Okay, so you can change the name of the molecule, no issue, but we are okay, it is done. So it has reported 10 molecules. So if you go back to our folder, this is docked out, right? With it inside the docked out, it contains the docking files, conformer files, and uh, the log file containing the scoring data, right? So in this top molecules, it will contain the top 10 molecules with their binding affinities, right? So in the next script, what it is doing is, it is looking for the top scoring molecules. Then according to this top scoring molecule data, it will extract the molecule in this folder. Okay, so it will look for the molecule in the this docked out database, okay, and then it will extract the top scoring molecule and keep it in the top dock molecule folder, okay. Then again it will convert the it will convert the PDBQT format into SDF format, okay. You can change any of the format, you can just keep as something mol2 or something also, right? So let's run this last script. So it's already picked up the molecule from this docked out folder and then store in the top dock molecules folder, which it has just created to store the top scoring molecule, okay. And it is also converted the PDBQT format to SDF format. So if you want to see, you can go to this top dock molecules and only 10 molecules are reported here, okay. So these are listed according to their highest scoring. Alright, so if you want to see this properly, you can open Maestro. So in the case of that particular Pyrex, okay, so in Pyrex also you have to export one by one, right? And again the SDF format that were generated from Pyrex, it was not able to import in this particular software, that is Maestro. Again you have to convert that into mol2 format, right? And if you are docking in Pyrex 10,000 molecules, you can't just do like that, okay. So one by one exporting and then importing, okay. So this scripts will make your life easier if you want to dock or do virtual screening for large databases. Let me just change this path to our working folder, okay. Import. Yeah, now you can just select everything, then import, right? So it will show you the conformers also easily, like, so this is for the first molecule and it is showing nine conformers, okay, like this first conformer. Okay, if you want to see the 2D interaction diagram, so the interaction, so some hydrogen bond interaction are there, and then some pi interaction are also there, okay. But I think the score is not that good, right? -9. Oh, this is 23, right? -7. So like this, you can also see the interaction as well as the scores of the uh, hits, okay, top scoring hits, right? Are you following, guys? You guys following? So if you have trouble in doing the steps, you can see the video and then again do the steps, okay. And again, if you have problem even watching the video and following the same steps, you can always connect with me. Okay. All right. So the docking using the script is done. So here it looks simple, and we have run the steps without any error. Okay, but when you are running alone, okay, obviously you will find some error. Okay, so try to see the error, what are the errors, and you can do a screenshot or can send me the error report. Okay, and most important thing where I've seen that all our students making mistake is when you are not keeping the configuration file in the same folder, and also the vina.exe file, the process ligin. Okay, those are the important things. Anyway, I will be sharing this particular file, okay, folder. So you can look it up in this folder, and also you can use this folder to do the docking again, repeat the docking again. Anyway, so let me come back to our next step. So now let's see if you have too many structure present. Okay, so let's say acetylcholinesterase that you want to search. Okay, so when you put acetylcholinesterase in the PDB, acetyl TYL choline esterase, right? So if you are searching like this, you are getting too many structures, right? If the your particular target is, you know, very popular and there is many people that are working on this particular target, right? So from here you can say that I want the Homo sapiens, and you see if you are doing docking and if the structure are available, then you should look for structure where the resolution, okay, resolution is less than 2.5. okay, so you can select from here 2.5 and that's it. Okay, so you can filter this out again to see how many molecules you can also see now. So there are 41 molecules, and this is apostate, and the method and resolution is 2.1, right? This is 2.3. So the first thing you have to see is your resolution. Okay, sorry. So resolution. Okay, so if you have molecule less than 2.5, take the best resolution. Okay, so first thing that you want to consider. But if you are looking for a particular complex with a drug molecule, then you have to look for that particular drug molecule. And let's say if you are doing in vitro study of fish Alzheimer, acetylcholinesterase, and you are working on and you are going to do docking on human acetylcholinesterase. Okay, their structure are different. Okay, if you are doing like that, then there will be a problem. Okay, so if you are doing a in vitro study for a fish acetylcholinesterase or any other organism, try to select organism for docking with similar or to what you are doing in vitro. All right, so you have to look for lesser or better resolution. Okay, so 2.5, below 2.5 is okay for docking, and if you have 1 angstrom or something like that for resolution, then it is still better. So what are the other things that you want to consider here? So if you go back to our slide, so you have to see, like, so let's open this. Okay, see here, where is that? Here you say mutation is 0. Okay, so you have to be very careful if you're working on a mutated version of your particular target. Okay, let's say you want to study, drug resistance for a particular drug target, right? And that particular mutation should be there, or otherwise if you are looking for studying a wild type target. Okay, so your target is wild type, and if mutation are present here and that also in the active site pocket, then whatever you are trying to do, the study that you are going to get from this will always be inaccurate, right? So if you are looking for validation of your in vitro work, or complement your in vitro work, you say that you are getting some biological activity against that particular target, and now you want to visualize how this drug molecules or the inhibitor binds at the active site pocket. Okay, and if you are using a wild type for your in vitro work, and in the in silico work, if you have not noticed, and then if you have used the mutated version of the target molecule that also in the active site, then the result that you get from in silico work will be incorrect. Okay, so you have to be very careful to see if if mutation is present, then what are the mutation, and should you go forward with the mutated version or not, and that depends on your study of interest. Okay, so you have to look into it. And also one important factor is this alternate conformation. Okay, so sometimes they are not able to when you do experimental uh, structure determination, like extracrystallography, they are not able to uh, clearly say that the side chain of this particular amino acid residue should be in this conformation or that conformation. Okay, so the occupancy, when you say occupancy, that is the electron density of that particular side chain residue. Okay, sometimes it is, if it is very flexible, then it is not able to tell that which position it should be there. Okay, so in that case they will give you two states or multiple states. Okay, conformational state. So if it is in the active site pocket, or even if it is not in the active site pocket, and after doing docking, if you want to use the complex for MD simulation, then during the MD simulation study it will create problem. Okay, or otherwise if it is the alternate conformation is present in the active site pocket, then also it will create problem. So what you can do is, let me just give you an example. Let's take the same molecule over this one. Okay, let's open it. Okay, so let's go to this protein preparation wizard. Let me show you what I am trying to say. Okay, so before that, let's just delete everything that is not needed here. Okay, others. Then also in protein we don't need the chain B, right? And this is the ligand, we don't need the B ligand. This 2 also not needed. Okay. All right. So we have cleaned the structure. And then if you go to this protein preparation wizard, let's uncheck this. If you have license, then you can keep this, okay? But we don't have license, so we are going to uncheck this all. Okay, others you can keep as default. And then press run. So I wanted to show you what does this alternate conformation means, okay? So after processing the receptor, okay, you go to this diagnostic option, okay, diagnostic, and here you go for this check workspace entry, okay, click this. In this alternate option you get this residue, okay, as the having alternate conformation. What does that mean? So when you click here, it will zoom into that particular residue and see this residue has two conformations, okay, one is here, another is here, okay. So when you do docking, let's say this is in the active site pocket, when you do docking, instead of one conformation it will be having two conformation, okay. So the docking result will be spurious, okay, it will be incorrect, okay. So you can have hydrogen bond interaction here maybe, but if this is in this particular conformation supposed to be, then the hydrogen bond interaction or the interaction that you are having with your ligand will be incorrect, right? So how do you solve this problem? And again, if you go back here, you see this is occupancy. That means this particular position is having like at 57% of the time when they were doing the crystallization process, they are this in this conformation, okay. But it's almost the same, it's like 50-50. This conformation, this alternate conformation, okay, is also in like almost like 50%, or it's almost like 50%, right? 0.43% of the time it is here like this. So which one should you take? Okay, you cannot take both the conformation if this is in the active site pocket and do docking, right? So which one should you take? So in order to do that, to check which one you should take, you can one more thing. So if this is like 80 to 40 or 80 to 20, you can take the 80 occupancy one. That is so easy. But see, this is like 50-50, all are 50-50 like that. So in that case, in this case, what you can do is you can go for a Rotamer library, okay. So in this Rotamer library, they are storing the sidechain conformers of highly crystallized, I mean very fine crystallized experimental structure of the proteins, okay. From databases they are collecting, and they are trying to see if they have this similar backbone, how is the conformation, or similar side chain, how are the conformer arranged, okay. So conformer that are arranged at that particular percent of the time at this particular position, it is likely that this should be the conformation in nature, okay. So how you can see that? So now I can go to this edit option and then go to this Rotamer, okay. Let me just select this one first, okay. Okay, something got wrong. Then we can start. Okay. Yeah. So automatically it should be selected because I was selecting the alternate and then the rotamer again. That's why it's giving problem. Otherwise, when you are just selecting this one, so when you did the check workspace entry and then selecting this one, after that, immediately after this, if you are going for that rotamer library, it will select the particular rotamer that you want to see, okay, or the sidechain that you want to see. So this is the original one that is highlighted here, okay, and this is from the library, okay. This is the conformer from the library. So how much percentage of molecules or sidechains which is having 15%, okay, of the database library is having this particular confirmation, okay, this first one, okay. So when I click this, you see this is the confirmation. So instead of the other one, you can take this somewhat similar, okay, so somewhat it's aligning. So you can take this one, right? So you can say that, okay, I want to take this, and then here you can say I want to commit, okay. So when you say commit, it will be keeping the one confirmation only, okay. And then the same thing you can do for the other alternate confirmations sidechains present, okay, right. So go to the edit again, rotamers, and see the highest scoring rotamer here, I mean highest percentage present conformer of that particular sidechain, okay, or the rotamer. So this is the first one, so it is almost similar, right? So you can keep this, and now you can say that I want to keep this one, so I will commit this particular confirmation, okay. That's it. Like this you can do one by one for all these alternate conformer that are present, okay. So this is one of the way you can do with PyMol as well as Chimera. They have all different steps, but for me I think this Maestro, I mean using Maestro, it is much more easier, okay. That's why I'm using this one. All right, this is you won't find this in book, okay, or I mean some publication will be there. So what we did was we did a study, okay. So we took the holo, means when you have the co-crystallized ligand, okay. So if you go back to the so here many are present, right? The human acetylcholinesterase complex with this particular molecule, complex with this particular molecule, complex with this particular molecule, complex with this particular molecule. So many molecules are there, okay. So if you want to do virtual screening, which let's say that they are also having good this thing resolution, right? All of them are having in the range of 2 to less than 2.5, right, angstrom. So now which one you should choose, okay. So do you choose donepezil, galantamine, or this other inhibitor complex? Which one, which complex should you choose, okay. So what we did was, you know, when we have this holo structure and many co-crystallized ligands are there, so we would like to select the crystal structure or the co-crystallized structure where the ligand is highly active, okay, so most active than the other present in the database. So we are not just saying like that. So we have some data also. We haven't published the data, but we have the data, okay. So some few more benchmarking we have to do. So what we did was we selected the structure, co-crystallized structure from the ligands. So we have the worst binding affinity ligand to the best binding affinity ligand, and we also created a database, active molecule database. So those molecules which are already known to be active, okay, biologically they have experimentally calculated or determined that those molecules are active against the acetylcholinesterase or your particular target molecule. So using those database of the active molecules, you did virtual screening or docking. Okay, so the docking done using the co-crystallized ligand with the most active molecule, it is able to pick up those um, highly active molecules from the active molecule database. Okay, when you do use the database of the active molecules as compared to the other molecule which are not that much active, but you have the co-crystallized structure of that average activity molecule. Okay, so we are consistently getting for different target. So I'm adding the information here also. It's up to you if you want to include or consider this information or not. Okay, so once we publish, then we can obviously can consider. So these are the other things that you have to look also. If there are missing residues, right? If it is in the active site pocket, some of the residues are missing, then or surrounding the active site pocket, then obviously you have to fill up those missing residues. You can do loop modeling, okay, if there are only few residues missing, or if large number of molecules or residues are missing from the regions, then you have to generate a model. Okay, so if the residue missings are too many, then you have to predict the structure of or the construct the structure of the target molecule. Okay, so if there are classes, you have to do energy minimization. This we'll do tomorrow. Okay, so without doing homology modeling proper step, then it will be difficult to model this missing residue steps. Okay, so let's do it tomorrow, and tomorrow we will try to do target active site uh, target prediction also. Okay, and then after predicting the target active site, we will do docking. Okay, probably tomorrow will take 2 hours. Okay, so everyone is gone, only two of you are left, huh? Is this too complex or what for you guys? Kamlesh? So for me, I am not using laptop. I am using a desktop, and its configuration is good. So I'm also using GPU. The processor is i9, and yeah, so and then memory RAM is like DDR5, and I think 32 GB, I think. But you can use simple office laptop also, but the thing is, if you are going to do 10,000 molecules docking using this script, it will not hang your uh, laptop. But since if you are not having a high configuration system, then it will take time, so you have to keep your laptop on for long time. Okay, so anyway, please try to practice. Okay, so theory, all those theories and all, when you practice, and sometimes if you are doing wet lab studies and if you want to publish work, whenever you submit the practical part or your wet lab study, most of the reviewers nowadays, they will ask for this complementary bioinformatics work. Okay, so in that case, it is always useful to have this uh, you know topics or whatever study you are doing now in handy. Okay, so once you have this basic command line command in your hands, then whatever the reviewer is asking, now you will be forced to do the advanced studies. Okay, so you will be forced to read, you will be forced to do. So whenever you are pressurized, you will be able to do most of the things. Okay, so for now, just repeat the steps I'm doing. If you are successfully able to run this, that is well and good. And if you want to implement with your structure, and if you I mean your target, and if you have problem, let me know. I can we can solve it together. All right, then tomorrow we'll do structure prediction using homology based modeling. You can use modular, and then switch PDBs, and then also AlphaFold. So we'll be using those three uh, methods, and then it will also cover the missing residue, the steps. Then if possible, we'll do the uh, the binding site prediction, okay, step. And in the next or the last session, we'll be doing the any query you have, or and after that, one more thing we have to do: image quality, publication ready image generation. Okay, so in the last session we'll be doing that. Yes, you have to work hard. Okay, it's not going to be easy if you are doing this for the first time. So its repetition is the uh, you know yeah, so practicing and repetition is the key. Okay, then bye bye. I'll send you the recording. Do see and practice again. Okay, thank you so much. Bye bye.